talk a little bit about temperature. Now, temperature is a measurement of the hotness or coldness of something. And temperature is always, excuse me, always measured relative to some kind of standard. So whether we find an object to be hot or cold is comparing that object to ourselves. Our bodies are regulated somewhere around 98 degrees. 98.6 is considered the standard. 98.6 isn't exactly where everybody is at all given times, however. But somewhere between 98 and 99 degrees is where we tend to have our homeostatic kind of position. That's where we tend to exist as far as the body temperature is concerned. Objects feeling hot or cold are dependent upon what their temperature is relative to us. So why does ice feel cold? Well, it's because it's at a lower temperature than we are. Why does tap water feel cold if it's coming out of the cold side? Because its temperature is lower than ours. Why does hot water feel hot? Well, it's coming out of the hot water tank. It's probably at a temperature greater than 100 degrees. It's going to feel warm to us. We can measure temperature using a thermometer. Thermometers are calibrated and regulated, in particular based upon the freezing point and boiling point of water. So a Celsius thermometer has set the 0 point as the freezing point of water and 100 as the boiling point of water. The Fahrenheit temperature scale is slightly different. 32 degrees for freezing, 212 for boiling. Now, as far as science goes, we're going to tend to shy away from the Fahrenheit scale. Couple of reasons for that. First of all, it doesn't fit into our metric kinds of understandings. It's not based on powers of 10. It's actually, based on 180 point differential between freezing and boiling as opposed to 100. And the other thing, the main thing that puts us away from it is we have no direct ties to energy on the Fahrenheit scale. On the Celsius scale, we can tie Celsius directly to another temperature scale called Kelvin. And the Kelvin scale is what we call an absolute scale. Kelvin scale is based upon energy. The more energy that something has, the more temperature it's going to show. And furthermore, on the Kelvin scale, temperature and energy are directly proportional. So if I jump from 100 degrees Kelvin to 200 degrees Kelvin, a doubling of the temperature also equals a doubling of the energy of those molecules. That's not true on the Celsius or the Fahrenheit scale. If I go from 1 degree Celsius to 2 degrees Celsius, there's not going to be a very noticeable change in the energy, certainly not a doubling of the energy. So the relationship between Celsius and Kelvin, degrees Celsius is equal to Kelvin minus 273.15. Which means we can also flip that around. Kelvin is equal to degrees Celsius plus 273.15. If we had to go between Celsius and Fahrenheit, we have to take a couple of factors into play here. We have to account for the difference in the scales. That's what the 1.8 is for, as well as the scalar difference between the freezing points. That's what the 32 is for. if we had to flip it around, it would look like that. Now, these equations between Celsius and Fahrenheit, we're not going to use them very often. Almost every measurement that we're going to take in lab is going to be in Celsius. It's going to be far more common for us to go from Celsius to Kelvin or Kelvin to Celsius than we are for Celsius to Fahrenheit or vice versa. I just gave you those equations as a reference point in case you had to, for some reason, do some kind of a conversion regarding that. And basically all that this slide is doing is rehashing all the information I gave you on the last one. So I'm just going to kind of skip over it here. We get to the last part of this chapter. Chapter 1.3 and 1.4 talks generally about energy and energy change and generally about the scientific method. If you've had any kind of science course before, you've probably seen most of these terms in some kind of way. But we'll start off with the basics and just kind of take it from here, make sure that we're all on the same playing field so that we can use these terms in future chapters. Energy. Energy, by definition, is the capacity to do work or to transfer heat. Now, in some cases, energy is used for both purposes. Work is done by something, and in the process of doing that something, heat is transferred from one object to the other. All of those involve energy transferences of some kind. Now, in terms of the types of energy, there are two primary types of energy that we would look at. The first is the kinetic energy. Kinetic energy is the energy of motion. All objects, in some kind of way, are exhibiting kinetic energy at all times. Because if an object is not at absolute zero, then at the very least, those molecules that make up that object are moving in some kind of way. They may not be moving much, they may not be moving fast, but they are moving in some kind of way. Even materials in solids are vibrating at some kind of level in the molecular scale and giving them some amount of kinetic energy. Potential energy is the energy that is possessed by an object based upon its position, and it can come in a variety of different forms. If you took a physical science class in high school, you probably thought most about potential energy in terms of vertical position. I'm holding a bottle, it has a certain amount of potential energy at this spot. It has a higher potential energy up above my head, because if I were to let it go from here, it would have much greater kinetic energy by the time it got to my hands than if I let it go from this position here. The further it has to fall, the more potential energy it has, the greater speed it will pick up as it falls to the ground, because it has more distance to fall and have gravity act on it. But there are other kinds of energies that fall into this kind of definition as well. We can talk about things like chemical energy. So if I have a substance, there's energy stored in the bonds of that substance. And when a chemical reaction occurs, that energy in those bonds can become released as the bonds break and reform new products, new substances. Other forms of kinetic energy can be things like mechanical energy, energy that is converted to do some kind of work in a machine. And electrical energy, heat energy, they all kind of fall from that idea. Now let's tie this back into chemistry. When chemical and physical changes occur, we have to understand that energy changes are also happening at the same time. And depending upon the process that is occurring, some of these processes are going to require energy to come in, and some of those processes are going to release energy as they go. So some quick examples of that. Combustion. If I have a bonfire and all of my friends are standing around the bonfire at appropriate social distances, the heat coming off of that fire is the direct result of a chemical reaction. The oxidation of the wood as it converts from cellulose to carbon dioxide and water vapor in this reaction is a very exothermic one, generates lots of heat as it reacts. In a different way, a cold pack, a chemical cold pack. What you have in a chemical cold pack is basically some kind of vessel that has a divider in it that separates the water component from this solid component. You pop the pack in the middle, the barrier goes away, the solid and the liquid start to mix and dissolve. The end result of that is that dissolving process actually draws energy from the surroundings. Draws in energy. Feels cold because it's drawing in energy from you as it sits on your arm, as it sits on your shoulder, as it sits on your leg. Now, the actual thing that's happening in there, the solid in there, is something called ammonium nitrate. The ammonium nitrate, as it dissolves in water, actually picks up energy from the water and uses it to break the bonds that exist between the ammonium ions and the nitrate ions inside of its crystal. And the overall net result is that it's drawing in energy as opposed to releasing energy. When something draws in energy, it feels cold to us. When something releases energy, it feels warm to us. As I mentioned before, kinetic energy is the energy of motion. And so the amount of kinetic energy in a sample does increase as the temperature does increase as well. Think about that example I gave you about the molecules vibrating inside of a sample. If I increase the temperature of a sample, all that's going to cause it to do is cause those molecules to vibrate faster, to have more energy overall as they're moving. Potential energy, I mentioned also. Position-based energy, stored energy is a good way to think of it. If I have an object and I'm just casually tossing it up in the air, there are a couple of things that are happening as this tossing is occurring. First of all, when this bottle is at rest in my hand, it is currently possessing minimal amounts of kinetic energy. Almost all the energy that is possessed by it at this point in time are potential. When I toss it, two things are happening. As it is going up, obviously it has kinetic energy as it is elevating and as it is falling, because it is in motion. As it is elevating, it is actually gaining potential energy from its increase in position until it reaches its apex. When it reaches its apex and begins to fall down, the potential energy that was put into it to get it up to this position starts to convert into potential energy, or excuse me, try that again. As it starts to fall, the potential energy is turning into kinetic energy, and the kinetic energy is causing the bottle to fall faster down than it was going up. Now, from a chemical point of view, high potential energy is also associated with reactivity. Things that are highly reactive also tend to have high amounts of potential energy. Things that are stable and unreactive tend to have low amounts of potential energy. And that's an important distinction to make, because when we start talking about chemical reactions, one of the main driving forces of chemistry and of chemical reactions is stability. Things react to become more stable than they were before. That stability is usually going to be accompanied with some kind of energy change, whether energy input or energy output, usually energy output of some kind. So this diagram here is probably a better illustration of what I was trying to do with the bottle here, in terms of showing how the energy transformations do change as a ball is tossed into the air and allowed to fall to the ground.